Hi, welcome to Real Learning Center. We are on our second video on 2D motion, two-dimensional motion, which is we have already now gone through what is meant by projectile motion, and we have seen that most of the projectile motions are when you throw a certain body when in the gravitational field, it goes through the projectile motion. It's called projectile, and then now we are going to talk about something called as circular motion. Circular motion is, as its name suggests, is circular in nature. Let's look at what are the things that we need to learn using circular motion. Okay, so now in the circular motion, most important thing is it is a periodic motion. You can actually watch here that the ball going around the circle and it keeps doing continuously the same thing. It comes back to the original position and then continues again. So it is a periodic motion. So circular motion is a periodic motion. Now, what about this? The earth, which is going basically rotating around its own axis. Is it a circular motion? Though it is not a circular motion, it is actually called as a rotational motion. But however, if you take one point, one position on the surface of the earth, let us say in India, Bangalore, one point, and that point, if you watch, it goes through a circular motion around the center of the earth. So circular motion, if you learn, we can actually apply that in rotational motion as well. So in every rotational motion, there will be circular motion. For example, you can see here, it is another kind of a interesting circular motion. There are lots of things happening here. So you can very clearly see that the center of the blue circle goes around the center of the other circle. Okay, and they are again going around in various different circles, multiple circular motions happening at a time. Okay, so here also you can see that there are actually several rotational motions happening, and if you take single particles on each one of them, they are actually going through circular motions. So the particles of any rotating object actually go through a circular motion. Hence, if we study circular motion, we can apply that into rotational motion as well. So though rotational motion and circular motion are different, but they actually work on the same principles. So let's look at basically circular motion in more detail. Now, let's look at basically two kinds of circular motions, uniform and non-uniform circular motion. Now, what is a uniform circular motion? You just watch it. So the one which you are seeing there, I am claiming to be uniform circular motion. Now the one here, just watch here, the other one is considered to be non-uniform. So see what is happening. The ball actually slowly slowing down. Okay, the speed of the ball is changing. Whereas in the first one, the speed of the ball is not at all changing. In non-uniform circular motion, the speed of the ball is changing. In this particular scenario, the speed of the ball is actually decreasing. But it need not be that so. The speed of the ball can be increasing. So ultimately, if it has to change, if it changes, speed varies. If speed varies, we call it as non-uniform circular motion. And if the speed doesn't vary, if it is constant, we call it as uniform circular motion. Okay. However, think about it. In both cases, the velocity is continuously changing. What does it mean? In the case of a speed, we only have the magnitude of the speed and how much it is moving in how much time. Whereas in the case of velocity, we are talking about the direction. You can very clearly see the ball at every fraction of a second, at every instant, the ball is changing its direction, and that is why it is velocity is changing. Velocity, even in a uniform circular motion, you can see velocity is actually changing, not because its speed is changing, but because its direction is changing. So that important aspect, please keep in mind that in a uniform circular motion, speed is constant, but velocity is continuously varying. So let's go a little deeper into the circular motion. Okay, uniform circular motion. Let's first talk about uniform circular motion. Here, I am taking it could be clockwise or anti-clockwise. I am taking here now anti-clockwise. Okay, so it is going through a certain path, circular path. and it is uniform. So we are going to define two things, angular displacement and angular speed, because we have already defined in earlier part of the motion where displacement and speed we have already learned. This is angular displacement and angular speed. What are they? So I will actually show it. I want to basically stop it at some point here and take a look at it. So let's stop it at some point here. Okay, and this I will call it as the initial point. So from there, let us say it has moved a little bit up like this. Okay. Now, if you actually join that point, now that line, the radius line, actually makes an angle theta. Okay. And that theta is what we call from the beginning. If this is what is our main position, original position. Now it has made an angular displacement. So it is called as angular displacement. Theta is nothing but angular displacement. Okay, and let's say it took actually some amount of time to do that. Okay, it took some time, like 1 second, half a second, whatever it is, to go from there to there, 0.1 second. So let's call it t. So t amount of time it took. So it made an angular displacement and it took around t amount of time. So in such a scenario, okay, we define for any uniform motion, we define it as angular speed is equal to angular displacement divided by time. So if you remember, our linear speed is nothing but linear displacement divided by time. So angular speed is angular displacement divided by time. So we use it as a new symbol we are going to introduce for angular speed. It's like a small w. We call it omega. Okay, omega is equal to theta divided by t, and we actually measure that using radians per second. How many radians? Because angle we measure in radians are degrees. So we can measure in this is a standard unit, which is radians per second. Okay, so this is called angular speed. Okay, and the angular speed we not only measure in radians per second, there are also other common units that we measure. So we will say angular speed also can be measured as how many rotations it has done in 1 second. RPS we say. Sometimes we use the word rotations per minute. See here, we are using the word rotation because rotation involves circular motion of some particles, of the particles. Okay, so it is RPM. So we use that also for talking about angular speed. Okay, so we have understood angular displacement and angular speed. Now we are going to basically try to understand the relationship between angular speed and linear speed. We always know what is linear speed. Linear speed is like magnitude of the velocity. We say v, velocity, and angular speed is omega. So what is the relation between these two? Is it possible to find out the relation? So let's see. We are going to basically again stop it here, and again let's say move it a little bit, and this angle is theta. Okay, at this position, if you see, after a small amount of time from here, so the small amount of time generally we call delta t. It has moved a little bit. Okay, let's say it moved a little bit. So you can see that arrow, small arrow. The small arrow is nothing but its linear velocity. It has moved linear displacement, not velocity, displacement. So I will call that basically as the angle it has covered while doing so is, I will call it as small angle called as delta theta, and that small displacement I am going to call it as delta x. Okay. Delta is a symbol, a small triangle kind of a symbol which we use to say small. Okay, the small, very small displacement delta x. So this is linear displacement. One of them is a line, you can see. The other one is an angle, delta theta. That's an angular displacement. So first what we are going to do is to find a relationship between linear displacement and angular displacement. Then we can find a relationship between linear velocity and linear speed and angular speed. Okay. So let's say this happens in a small time delta t, and the radius is is r. Okay. So radius is r. I am using all variables and not constants. So we need to get used to that in physics. Okay, we will be. I will not be using all the time examples of numbers. I will be using variables. Okay, so delta x and delta t is there. So in delta t time, delta x it has moved, and the angle it has covered is delta theta, and the length of the radius is r, 5 centimeters, 10 centimeters, basically r. Now, the things we know, what are the things that we know? We already know linear speed. So, what is linear speed? For us, linear speed is simply distance travelled divided by time. The distance travelled here is it has moved some distance delta x. Time taken is delta t. So, we can say angular the linear speed is delta x by delta t. We know that. Okay. Similarly, angular speed. We just now learned angular speed. Angular speed is nothing but angular displacement divided by time. So, these two things we know, just now learned. One more thing we know from the geometry. Okay. In geometry, if you want to relate the arc length to the angle, there is a relationship. Arc length, the small arc length, the delta x, is related to the angle, which is in radians, theta. Radius into the angle will give you the arc length. So, these three things we know. From this, we can make the relationship between speed and angular speed and linear speed. So, how do we do that? We are going to write down in the form of equation. First one, we say V is equal to delta x by delta t, which is linear speed. Okay. Second one is angular speed, which is omega. What is that? That is delta theta by delta t. Just now we have learned theta by t in the just the previous slide. So, this is delta theta by delta t, because that much it has moved in angle. And then we also know arc length in this case is delta x. So, which will be equal to r into delta theta. That is the third one, blue one. So, we know these three things, which basically V is equal to delta x by delta t, omega is equal to delta theta by delta t, and delta x is equal to r into delta theta. Using these three things, just rearranging the terms, we can get our final result of angular speed and angular speed and linear speed relationship. So, let us write down the first one as it is. V is equal to delta x by delta t. Now, what I am going to do is, I am going to find out where the delta x is. Delta x is there in r into delta theta. So, I will go to r into delta theta, okay, and move that r delta theta, replace the delta x by using that. So, I will get r into delta theta in the place of delta x. So, you got now r into delta theta divided by delta t. So, we look at this part, delta theta divided by delta t. So, that we already know what it is. That is nothing but omega. That is omega for us. That is angular speed. Now, suddenly we are getting now relationship, which is V is equal to r into omega. So, V is equal to r omega is the formula that we have to remember. All the time when we want to basically convert angular speed into linear speed or vice versa, we can use this relationship. So, this is one of the most important fundamentals of circular motion. So, there is one more fundamental of circular motion, we will go to that now. So, now let us understand linear velocity. Okay, we now talked about linear speed, we talked about linear speed and angular speed. Suddenly now I am moving into linear velocity. Okay, is linear velocity constant during circular motion? That is the question. So, which we have answered. Linear velocity is never constant. Okay, it is changing. Why? Because the angle is changing. Let us see how. Okay, so I am going to basically stop it at some point. Okay, and again do the same thing. Okay, it has moved to some point here, and I am going to show you here that this is my radius vector, and then if it has moved a little bit, okay, that is actually delta x. Okay. Now, that delta x, I will call it as delta x1. Okay, the movement, a little bit of movement, first time. In delta t time, delta t1 time, delta x1 it has moved, delta t1 time it has taken to move. Okay. So, what is the linear speed? Linear speed is delta x1 by delta t1. Okay. I just use different variable. Now, if you actually make the ball move a little bit more, in the next some amount of time, let us say delta t2 time, okay, then that distance what it has moved there is delta x2 in the time delta t2. Now it is again straightforward. The linear speed at this point when you want to calculate is delta x2 divided by delta t2. So if you actually do this, and if it is a uniform circular motion, means speed is not changing, in that scenario, these two values happen to be equal. So if these two happen to be equal, delta x1 by delta t1 and delta x2 by delta t2, both of them are equal, okay, then we can say that linear speed is constant, not changing. Everywhere, wherever you go, linear speed is constant. So that is the meaning when I say linear speed is constant. Okay. Mathematically, it is delta x by delta t, wherever you take is constant. Okay. Now, however, can we say the same thing about linear velocity? You can very clearly see in the linear velocity scenario, the angle of the delta x1 and delta x2, the angle, they are not actually in the same direction. They are slightly different direction. So direction is continuously changing as the ball is moving. Hence, linear velocity is not constant. Linear speed is constant. Linear velocity is not constant. Now, once we say that, so now we'll get back to our Newton's laws, okay, and also basic kinematics. If we say the velocity is not constant, velocity is varying. That means there must be certain acceleration. So if velocity is not constant, there must be certain acceleration. And if there is acceleration, then Newton's second law tells us that there must be some force. Without force, there can't be acceleration. So what is the value of acceleration here? And where is this force? So if we understand these two, we get a clear understanding of circular motion. Okay. So now our question is, we know that linear velocity is changing. If linear velocity is changing, there must be acceleration. Some acceleration is happening, and if there is acceleration, there must be some force. So we will see what they are. If you look at, let us say when the ball is not going to move automatically like that, somebody is rotating it like this, let us say, then it is moving. In this scenario, if you carefully watch, okay, the ball is tied to a rope and he is basically rotating it, and that rope actually gives a tension force. Okay, it pulls the ball towards the center. Okay, here the crux is the word center. It pulls the ball towards the center. And not only here. So here the rope is connected, but we can see a circular motion when rope is not connected also. Like for example, okay, sun going around the earth or moon going around the sun. Their rope is not connected, but still there is a force, and we call that force as a gravitational force. So that gravitational force pulls it towards the center of the sun. Okay, the earth, gravitational force of the sun pulls the earth towards the center of the sun. So this force towards the center is called centripetal force. The force that is towards the center is called centripetal force. And whenever there is a force towards the center, okay, acceleration will also be towards the center. You can see very clearly here. The force is towards the center. Now, according to Newton's second law, the direction of the force and direction of the acceleration have to be same. Hence, acceleration also will be in the same direction. That is why we call them as centripetal acceleration and centripetal force. Centripetal means towards the center. This acceleration is towards the center. However, remember that our linear velocity is not towards the center. It is in this direction. It is like a tangential to the tangent of the circle. It is perpendicular to the acceleration. So whenever velocity and acceleration are perpendicular, it's a very strange thing. Okay, velocity is in one direction, acceleration is perpendicular to that. Whenever that happens, then the body actually rotates with uniform circular motion, where the velocity will be continuously changing, but speed will not be changing. Such a scenario is basically possible only in what we call uniform circular motion. So in a uniform circular motion, you can see force is towards the center and hence the acceleration is towards the center. And hence also here the acceleration does not change the magnitude of the velocity. The acceleration changes only the direction of the velocity. So remember this, in a uniform circular motion, acceleration changes only the direction of the velocity. Now, if the value of this acceleration is related to the radius r and the velocity using a formula. Okay, I will give you that formula, though I am not going to prove it now. So the formula is called A is equal to V square by R. If given V and R, one can calculate the acceleration. R given A and R, one can calculate velocity. So these are the various ways. This is the way of actually relating the velocity and acceleration in a uniform circular motion. Once you know acceleration, then you know what is force also, because we know Newton's second law, which is force is equal to mass into acceleration. Force is equal to mass into V square by R. So centripetal force is always equal to mv square by R, and centripetal acceleration is V square by R. When we get into doing some interesting problems, we are going to use this formula. So I am not going to derive this here, but in another video I would probably do that. Okay. So we have now understood the basics of what is called as a circular motion. That too, we actually dwell, we were delving deep into uniform circular motion. We have not talked about non-uniform much, okay, because that is not used much in our analysis. So uniform circular motion is understood. So that brings us to the basic concept of 2D motion is ended, and moving forward, please watch videos on other physics topics. Thank you.